Okay, so here we're going to look at the vertex form of a quadratic function. Now this is whenever the quadratic formula or quadratic function is in the form of a times in parentheses x minus h squared plus k on the outside, and h and k happen to be the vertex of the parabola. Another way of looking at where the vertex is just applying transformations. Typically the vertex of a parabola is that point right there, which is the order pair 0, 0. Then whatever you have inside would affect the transformation or the order pair in the opposite way, hence the minus sign in the formula for vertex form. And whatever's outside affects the y value in the same way that appears. Because the vertex is originally 0, 0, multiplying by a would not have any effect on the vertex, but does affect the rest of the graph. So in this way we can use transformations as well, and essentially vertex form is when you use transformations. And you can also just use the dilation caused by the a, as well as the vertex to find the graph and characteristics about the graph. Okay, so in this example we're going to be describing transformations of the graph of f of x equals x squared to form the function g of x, which is equal to negative 1/2 times the difference of x and 3 squared minus 2. So if I go through and do this, I'm going to stick with my normal way of approaching this, and that's just using transformational rules here. So whatever's inside will affect x in the opposite way. So we see x minus 3. So what's really going to happen to x is we're going to take x and add 3. And then the stuff outside affects y. So we have the multiplication there and the subtraction there. So we are going to take y, we'll multiply by negative 1/2, and then we will subtract 2. Remember that it will follow order of operations for the outside stuff, while the inside stuff goes in reverse. Now that we have that, we just have to figure out what types of transformations do we have. Well, first of all, are we multiplying? Yes, we are multiplying y values by a negative 1/2. So that creates two different transformations here. Because we're multiplying by a negative number, it creates a reflection. And that reflection is going to be across the x-axis, since the y values are what's changing. And now we are also multiplying by the 1/2 as well, so that creates a dilation, which will be vertical. This specific dilation will be a compression, because the factor that we're multiplying by is a factor of 1/2. So we have a vertical dilation, or vertically compressed, by a factor of 1/2. Now we also have to check for addition and subtraction. Addition and subtraction creates a translation, and yes, we do have addition and subtraction. So the graph is going to be translated. Since we are adding 3 to x, it's going to be 3 units to the right, according to our rule. And we're subtracting 2 from the y, so 2 units down. And there we go. Now here we're just introducing some of the key characteristics of the quadratic parent function. So the quadratic parent function has this U-shaped graph called a parabola. It has an axis of symmetry which runs along the y-axis and goes through the vertex, which is also the extrema. The vertex is originally at 0, 0. Our axis of symmetry is originally at x equals 0. Domain for a quadratic is all real numbers, which is between negative infinity and infinity. Just several ways to write it over here. And then the range is originally y greater than or equal to 0. And of course, there are various ways to write that. So that's some key characteristics of the original parent function of a quadratic. Now in this example, we're going to be going through and applying transformations to key characteristics. Transformations can apply to some of the characteristics, but not all of them. So just starting off with domain, I'm going to write the original domain and stuff in red, while my transformed one will be in a different color. First of all, I'm going to figure out my transformations. So inside affects the x values in the opposite way. So I have x plus 2, which means what we're really going to do is x minus 2. Outside affects y in the same, so we have multiplication by negative 3 and adding 1. So we're going to multiply y values by negative 3, then add 1. Okay, so starting with domain. Domain here is typically all real numbers for the original parent function's domain. So if we transform this and our x rule of subtracting 2, if we subtract 2 from every single real number, we're going to end up with still having all real numbers. The domain of a quadratic, unless it's intentionally restricted, is just all real numbers. Now range is a little bit different. Range starts off for the parent function as y greater than or equal to 0. The y values, we are doing two things to them. We are going to multiply by negative 3 and then add 1. So we're going to multiply all the y values by negative 3, and that's going to turn our new range into, well, multiplying 0 by negative 3 doesn't actually do anything. But when you multiply an inequality by a negative with inequalities, it flips the inequality sign. And then after multiplying by the negative 3, again, 0 times negative 3 is 0. Plus 1 is what we still have to do, which puts us at 1. So this graph has been flipped and slid up by 1. So you can kind of picture the graph as what's happening if you understand transformations really well. The next we have the vertex. Vertex is typically at 0, 0. And we just apply our transformations to that. Even without looking at the graph, we can figure out what the vertex is. Our x transformation is to take x and subtract 2. So 0 minus 2 is negative 2. And our y transformation is to multiply by negative 3 and add 1. So 0 times negative 3 plus 1 would be 1. The axis of symmetry is typically for the parent function, x equals 0. Since this is an x descriptor, we apply the x rule, which is to take x values and subtract 2. So if we subtract 2 from x, we're going to end up with x equals negative 2 now. So that's where the new axis of symmetry would be located. And as you can see, it still goes through that vertex. They share that same x value. We have one more thing on this list to do, and that's extrema. Extrema was originally 0, 0. It was originally the same location as the vertex, and it's originally a min for a quadratic's parent function. If we apply transformations, well, the ordered pair is now going to be the same as what it is for the vertex, negative 2, 1, for the location of the extrema. However, we have to figure out if this is still a maximum or minimum. Well, the only thing that's going to change that is a reflection across the x-axis. In other words, multiplying y values by negative. Since we do indeed multiply by negative 3 here, that's going to change the graph from being upright to being downwards, meaning we will now have a maximum instead. Now you can also apply transformations to some of the other key characteristics that we've discussed. You cannot do it, however, for positive, negative, x-intercepts, or y-intercepts. Those don't necessarily follow transformations. In some cases they might line up, but not always. The only other one that we can actually talk about is the intervals of increasing, decreasing, because that typically deals with the extrema, versus positive and negative dealing with the x-intercepts, which don't follow transformations. For increasing, decreasing, originally the increasing interval would be from 0 to infinity, while the decreasing interval would be from negative infinity to 0. If we apply our transformation rules to this, so first of all, I'm going to deal with the interval. So my interval for x, and remember the interval has both x values here. So interval, if I subtract 2 from each x value, so 0 minus 2 is going to be negative 2. And infinity minus 2, well, that's still going to be a really massive and incomprehensible number. And then similarly for decreasing, subtracting 2 from negative infinity, still just negative infinity. And subtracting 2 from 0 would put us at negative 2. We just have one more thing to deal with, and that's whether it's still increasing or decreasing. Well, as mentioned before, just like with extrema, switching from min to max, if we have a reflection, it's going to flip the graph, meaning what was originally going down is now going up, and then what is originally going up would now be going down. So the first one, while it was originally increasing, is now the decreasing interval, and the second one, which was originally decreasing, is now the increasing interval. Okay, in this example, we're going to be writing the equation for the quadratic function with a vertex of 3, -5, and a y-intercept of 13. Well, with that, I do want to mention, first off, that y-intercept as an ordered pair is the point 0, 13. And that's going to be important later when we go down the road. I can approach this by using the formula f of x equals a times x minus h squared plus k. Or I can just approach it with transformations. I usually just approach it with transformations. So normally the vertex of a quadratic is 0, 0, but now the vertex is 3, -5. So the vertex is unaffected by dilations or reflections. So from this, I can glean that the translations is x plus 3. We're adding 3 to the x values, translating it right 3, and y minus 5. So those would be the translations, and then just following that logic, inside affects the x values but in the opposite way. So if my rule is x plus 3, then my equation will say x minus 3. And y is the outside stuff and in the same way. So since my rule is y minus 5, there's going to be a minus 5 out here. So now all we have to do is figure out what the value for a is, or what the dilation is. So whether you just plug it straight into this formula or just use transformations, you end up at the same result here. You still have to figure out a, and we're going to do that just by plugging stuff in to find the value for a. And that's where this other point comes in handy. We have both an x value and a y value. We'll just plug those in for x and y and solve for a. So y is originally 13, x is 0, and we'll just go through and solve that. 0 minus 3 is -3, bringing everything else down. We got -3 squared, which is positive 9, so we have 9a. I'll try to make those distinguishable. And then it's just a two-step equation from here. We will add 5 and get 18 equals 9a, and then divide both sides by 9 so that we get the value of a, which almost looks like a 9 itself, is 2. But we're not quite done. Remember, our goal wasn't to figure out what the dilation was. This does mean it's been stretched vertically by a factor of 2. Our goal, however, wasn't that. It was just to write the equation. So we have y equals 2 is the value for a, x minus 3 squared minus 5. And that's the equation that has a vertex of 3, -5, and a y-intercept of 13.